I got a similar situation. This class, basically, we want to cover 2 more chapters before before the midterm exam. So today we're going to talk about transmitters, chapter 8. So let me stop sharing. So today we will have a chapter 8. Next week we will have chapter 9. And that 2 chapters will pretty much end the old technology. We will have a little bit of introduction for the new digital technology, but mostly those 2 chapters talk about old technologies.
Okay.
So then we have a midterm exam on next week. It will be similar. I will do an online on Canvas, and I'll give you a timer, for example, 2 hours or 1 hour for you to finish those exams. That's first. So let's move right into the transmitters. And we have 5 topics today, 236. So previously, we have covered the topic of 2 ways to modulate. These 2 methods are important. AM, FM, they are old, but they form the foundations of even the most complicated radio we use today. 5G, for example, still relates to the old technology. So AM and FM. So what about transmitter? Transmitter is still used quite often, those analog ones. For example, you have walkie-talkies, the police radio. Those are basic transmitters. So also, many of them became digital. So we will also talk about a brand new technology called the QAM. It's based on AM, but we added 1 extra word to it. With QAM, it turned out, is the technology used for all the modern digital radios. It can be your cell phone, it can be your cable modem, DSL modems, Wi-Fi technology, high-speed Wi-Fi. They all use QAM. So obviously, QAM is today's most important technology. It's based on AM, so we will cover this new topic with QAM. So first, for example, the fireman, the police radios. Today's radio, there are 2 types. The first type called FM. The second type is SSB. SSB transmitter. So those are the 2 most popular voice communication, analog communication. So for the FM transmitter, this is a typical diagram for FM. Let's start it here. This is a microphone. So you talk on the microphone, audio amp, do a little bit of processing to modulate a carrier. And then the carrier is multiplied. That means if it's 1 megahertz, you multiply 3, became 3 megahertz, multiply 10, became 30 megahertz, multiply 10, became 300 megahertz. And then the 300 megahertz will be the radio signal came out through this amplifier. So that's a typical design for FM radio, today's technology. There are many reasons we do a low frequency modulation, then multiply. One main reason is to get more deviations. Every time you multiply, you double the deviation. That means you change the carrier frequency. So if the carrier frequency changes 1 Hz here, after you multiply 60 times, the deviation will be 60 Hz. So if the variation is 10 Hz, multiply 60 times, it will be 600 Hz. So we create this wide frequency swing through this multiply technology. So multiply is preferred. We modulate at lower frequency than multiply, which create larger deviation, and then we have a current. Another reason, another thing is we see FM, but here is phase modulation. So this modulator actually is a PM, not FM. It turned out PM and FM are very closely related. So that's why we do a speech pre-processing here. We just alter our speech. So when the audio phase modulate, the end result is FM. So this is actually a math problem. Mathematically, if we do a PM here, but we alter our audio, the end result will be FM. So we do a pre-emphasis, a kind of filtering for our speech. And then the end result here will be FM. That's another detail about this system. PM, the end result is actually FM. And then we multiply. The SSB radio, modern SSB radio, follows this design generally. Again, we have a balance modulator. Balance modulator will be creating DSPs, double sideband. So this is the AM modulator. The AM modulator without carrier. So the carrier is cancelled. And once carrier is cancelled, we do a filter. That means remove the half of sideband. So if we talk about AM, we talk about this. This is a typical AM. We have a carrier, we have a lower side, we have upper side. This system, the step number 1, we do not use AM modulator, we use balance modulator. Carrier is removed, so we get rid of carrier. Step number 2, we use a filter. The filter will remove one sideband. For example, we will remove the lower sideband. So lower sideband is removed. Now only, so this is called SSB, single sideband. SSB technology, SSB is preferred because it conserves bandwidth. It only uses half bandwidth because we do not transmit lower sideband. We only transmit half the bandwidth, so it conserves bandwidth. Second, because the carrier is cancelled, we conserve energy. So SSB is preferred. So that's SSB. The SSB signal, that's low frequency SSB. So this is the modulation happens at the lower frequencies. The carrier frequency is lower. And then we shift this second mixer. We'll move it to a radio frequency and then goes out. So this is a horizontal shifting carrier from lower frequency to higher frequencies. And after that, we will send it out after the power. So this is a power amplifier. After the power amplifier, we go to the antenna. Now we are talking about a modern radio called the QAM. So this is a modern transmitter. It turns out almost all the modern transmitter is some kind of variation of this transmitter. So this diagram is kind of important because it's modern digital transmitter, including your 5G or 4G cell phone. So what happens is you have a couple of data, serious data. They were divided into half and half. One one is called I, one is called Q. So if data is 10 kilobits per second, so it will divide it into I and Q. What will be I? I will be 5 kilobits per second. Q will be 5 kilobits per second. So the data rate after the division, after you separate, will be half. So data rate is half. I will be 5K B per BPS Q. And then we go to analog to digital to analog converter. If the digital analog converter is 1 to 2, 1 bit digital to analog converter, 1 bit digital analog converter. So this digital analog converter, another digital analog converter, both are 1 bit. That means what is a 1 bit analog digital analog converter? 1 bit analog converter is just nothing. It's not a converter at all. It's just goes straight through. If it's 1 bit, and then we actually can go this signal go right through. 1 bit means no conversion. So it will go to the mixer. It goes to a mixer. And that's an AM modulator. That's a conventional AM modulator. So we have a 2 AM modulator. That's where the QAM name, the AM came from. Because we are using 2 AM modulator to modulate the data stream I, the second AM modulator to modulate data stream Q. So data stream I and data stream Q are both modulated by conventional AM modulator. Here is the difference. The first one is modulated by the cosine. The second one is modulated by a sine. So that's where the Q came from. Q means quadrature. That means 90-degree difference, phase angle difference. A sine and a cosine has 90-degree phase angle differences. So they are modulated by the same carrier with 90 degree. That's where the Q came from. So we have a cosine modulate I, we have a sine modulate Q. What happens after that is we add them together. That's called QAM. So QAM is basically add a cosine with a sine. The cosine will be AM modulated. The sine will also be AM modulated. The 2 AM signal add together, we got QAM. So QAM basically the sine multiplied plus cosine, sine plus cosine. So I will do a demo here. So if you study math, what is the sine multiplied cosine equals to?
I don't know. Can't remember.
I remember. Nobody remember that. Let me do a demo. Then we know. So let's find a sine. That's a sine. And then we will do a cosine. We'll do a cosine. So we have a sine right here. And then we have a cosine right here. We put a 90-degree phase angle, so that's a cosine.
Yeah.
Sine and the left is cosine. So let's go to slope and look at the sine first. Then we look at cosine. So So this will be a sine, and then let's look at cosine. So we got a sine, and then we got a cosine. What is the add them together? The red one. Another sine. But the phase angle notice is 55 degrees. So the only difference is the phase angles. So you see the red one. So we got a sine, we got cosine, and we add together is another sine with a phase angle right in the middle. So this is the initial phase angle, this is another phase angle. And the addition, the phase angle will be right here in the middle. So that's a sine. So that's QAM. So the red one is actually QAM. But we do not call it QAM because originally the both signals are only sine, cosine, not AM. So we will change the yellow to AM. We'll change the blue to AM. So let's go back to our signal generator. We will modulate this. So we will do a modulation. So we will do a AM modulation with a square. We will do another modulation here with a square. We will do two modulations. And I will put lower hertzes like this. Let's see what happens. Let's see what happens. So let's look at the first one, the yellow. Let's make it stronger. The modulation is not as strong, so we make it, for example, 50%. 50%, okay, 30%. Let's use 30%. So it's a 30% modulation. So if you look at it, that's the yellow. So let's make it so this is the yellow, and let's look at the blue. That's the blue. Let's make it bigger. Yeah. So we are modulating the two signals using one is the yellow, one is the blue. And now we are looking at the QAM, the resulting QAM, which will be the red signal. So now we are looking at the red. So that's the red. Let's look at more detail. So notice the red signal that changes, and that's QAM. So right now we are looking at QAM. And let's look even faster. So that's QAM. So it's almost look like AM, but one significant difference is its phase angle also changes. If you notice, the sign started at a different location. You see, the phase angle changes. So QAM is an AM signal because we are adding sine and cosine. Not only the amplitude change, the phase angle also change. So that's QAM. Is AM signal, amplitude changes, and the phase angle changes. If we are doing 1-bit analog digital converter, it's called the full QAM. So because we are having four patterns in, let's illustrate all four patterns. Let's increase the speed of our signal to 1.25K. That's what I was looking at. 1.25K. Let's change this to 1.25K. So now let's look at QAM in high speed. Previously, we are looking at QAM in very low speed. So we will see 1 second of one sine followed by another 1 second of one sine. Now we speed it up to 1.25K. The square be 1.25K. Now we are looking. So if we do a single, so this is what it looks like. QAM looks like. This 10,000 hertz carrier and 1.25K modulation. So notice this sine has phase angle changes, also has amplitude changes. Phase angle, amplitude, phase angle, amplitude. So that's what the QAM looks like in real world. We have two AM signals. If you look at the yellow and the blue, it's just AM. Let's look at the yellow. We are using sine, no sine. We should go back to square. Square, okay, 2 squares. Should be squared. This showing sine, I don't know why. But so this is the AM signal. If you look at the blue, it's another AM signal. So that's another AM signal. So both yellow and the blue are normal AM signals. Once we add the yellow and the blue together, we got the red signal, which is the QAM. That's QAM looks like. It has phase angle changes. It also has amplitude variation.
The phase on the blue one, it's at 120. Shouldn't it be at 90?
Yes, should be 90, but I found 120 is the computer has a delays. Yeah, in theory should be 90.
Okay.
But when I found when I put 120 difference, it's looks more like 90. So that's one change I did before class. Yeah, you got a very good point. Very good point. Do another sampling, 5K. Yeah, that's the AM looks like. What the QAM looks like. So you get the phase angle changes. You notice here the phase angle changes, and also amplitude changes. 10 kilohertz, 10 kilohertz.
The amplitude index is different. One's at 30%, one's at 70%.
Yes, I use that to modulate the two level here, Yes, that's another thing I did. So the AM signal will be at different levels. Yeah, this will be 30% of modulation index. This will be 70. That's nice. So this one modulate the AM a little bit smaller. This modulate a little bit higher.
Okay.
Yeah. So altogether, we have 4 patterns. So 4 patterns, that's called the called QAM. So 4 different patterns. It takes some thinking and some good demos to actually have a better understanding of QAM. Anyway, that's a QAM signal we have right here. And if you look at the spectrum of the QAM signal, we can also see the spectrum. Yeah, that's a spectrum of QAM signal. Let's do another sampling and then do, so this will be 10K. Let's do slower, 50K. Do a single one. My computer is doing something strange right now. It's not listening to me. While my sampling rate is 50K, the top bandwidth FFT should be 25K. Now it's 100K. Something is not going right, but you got an idea. Here is correct. So this is a QAM spectrum. That's another thing I want to point out. For QAM in spectrum in frequency domain, the upper side, this is the lower side, this is the upper side, is not identical. If you look at it, the upper side is actually stronger than the lower side. So let's get even closer look. So this is the upper side, this is lower side. So you see the lower side and upper side is off, is not identical. Previously, all the AM signals, upper side and lower side are mirror images of each other. This is the carrier. For QAM, the upper side and lower side is not the same. That's because of the addition they did. We add a sign with cosine. The end result of adding sine with cosine is not upper side, lower side will be different. So that's a QAM, very important topic. I hope I wouldn't expect the QAM idea will get through just one lecture session. So we will go back talking about this QAM repeatedly. Hopefully get that more comprehensive about the idea, more understanding. All right, let's move on to the next topic. The next topic is how to create a carrier. There's many different ways. Most popular method is a crystal. The crystal oscillator is a single frequency. For example, if you look at this crystal, it's a 44 megahertz. What's nice about crystal oscillator is it's extremely stable. So the frequency will remain 44 megahertz with almost no variation. So that's an excellent oscillator. But the problem is it's a single frequency. If you look at a modern transmitter, you might need multiple carriers. For example, I need 108, 110, 112, 114. I need a bunch of carrier frequencies. So how do you start it at 44 megahertz and get those results, 100? So we started with 44 mega, but what we really want is 100 mega, 102 mega, 104 mega, 106 mega. How do we go from here to here? It's going through a synthesizer, frequency synthesizer. So the frequency synthesizer get the job done. It will synthesize the exact carrier frequency we wanted out of single frequency. The single frequency came from the crystal. So how do we do this? There are a lot of details. I will not go into all those details. The detail is a PLL. Most popular frequency synthesizer is a phase lock loop synthesizer. So that's a PLL device. That's a PLL device. This PLL device will multiply the frequency by 100. So if we started with 100K, multiply by 10, multiply 10, this PLL. This is a PLL right here. This PLL will multiply frequency by 10. So the output will be 1 milli. So if you started with 44, the output will be 440 because we multiply by 10. Now, that's multiplication. Sometimes we also want addition. So this is addition. This is still multiplication. So it multiply twice, m and n. So multiply m, multiply n. So this is even more multiplication. So we started with 30K, ended with 389.74 million megahertz. So that's multiply. Sometimes not only we just want multiply, we also want addition. So we can get this, for example, for additions, and divisions. So there are many different ways to synthesize. Through this PLL device, we can do frequency multiply, frequency division, and frequency addition. We can do with that. That means we can start it with one single frequency. We can get dozens of different carrier frequencies out of this synthesizer. So that's the first topic. First synthesizer, because the detail, actually before we start class, I was thinking about going into the detail. Then I realized nobody will remember the detail anyway. So I will just skip the detail. if you're really into the design of PLL synthesizer, you will look at the detail. It's not difficult. You will spend half an hour if you understand it. But if we spend half an hour now, it's a half an hour wasted because you will forget about it, never use that because you never design a synthesizer or need to do. So that's our first topic. Second topic called DDS. DDS is even simpler. It's basically a computer will provide the binary data, and the binary data goes through a digital to analog converter. It will create whatever signal we wanted. A perfect example of DDS is this box. I am creating many signals using this box. All the signals I'm created on my function generator is a DDS. So if I go back to my function generator, so if I go to the web, turn one off, I will turn off. So I want to create a sign, AM. So I'm creating an AM. So this AM I'm creating right here is all came from the computer. The computer will calculate. Let me give you. Let's look at the yellow signal. That's AM signal. Well, when we look at it more closer, we found, yep, that's every dot right here is a number created by computer. So the computer will create all those binary numbers, and those binary numbers then go to digital to analog converter. And after the digital analog converter, you get your whatever signal we want to create. This is the signal we want to create. So all the signals created by this box is using DDS. It's called a direct digital synthesizer. To be able to do DDS, there are two conditions. First, you need a super fast computer. That computer have to create, if you want a million hertz sine, you want hundreds of millions of data per second. That has to be created in real time by your super fast computer. Second, you need a fast converter. Because if your converter cannot convert that binary data quickly enough, you still do not get that signal out on the other side. So once you have a fast computer, fast converter, fortunately, today's computers are all very fast, and so does the converter. So now the DDS became very popular because we have a fast computer and we have fast converters. So that's another example of DDS. This is the computer side, that's the converter side, and that's your output. You can create any sign, any signal, not necessarily sign. So that's our second topic. Second topic, we covered how to create a signal, either DDS or through synthesizer, PLL synthesizer. PLL synthesizer is an old technology. The DDS is the new technology because it involves high-speed computer. The number 3 topic will be the power amp. Power amp is also an important topic because we dealt with efficiencies, most importantly. Power amp, when we talk about power amp, we want efficiency. We also covered many different types of power amps. This is called the type A. Okay. Class A. Class A power amp. This is called Class B power amp. The Class B power amp is more efficient. We all know. The Class A, 50%, 50% efficiency. That's in theory. So let's look at this Class A amplifier, power amp. In theory, 50% efficiency. In practice, 25% efficiency. So what does that mean? That means a huge waste of power. So if your transmitter send out 100 watts, if the efficiency is 25%, 300 watts is wasted on your power amp. And your power amp basically became a huge heater. And most 25 on radio, 75 on amplifier as a waste. So that's a terrible technology. Nobody uses it. How about Class B? Class B is good. In theory, 70%, 80%. In practice, 50%. So Class B, in practice, half and half. So if you're broadcasting 100 watts, we are talking about 50 watts on the transmitter, on the power amp. Again, a huge waste of energy. Almost all the audio amplifiers are Class B. So if you listen to your radio, the speaker has 10 watts, that means the amplifier has 10 watts. Because this audio amplifier is type B. Most audio amp type B. So 50% efficiency. If your speaker has 100 watts, that means another 100 watts is on the amplifier. So Class A, Class B, both are no good. So does Class AB, no good. 50% of efficiency. So that's why we invented Class C, Class D, Class E, Class many other classes. So Class C can reach almost 90% efficiency. So Class C is much better, big improvement. But it's not the best. The best is after Class C, called the switching power amplifier. Switching power amplifier is a new type of amplifier. This amplifier signal not by linear. These are called linear amplifiers. Linear. These are classical amplifiers. But the modern amplifier are called the switching power amps. Let's give you an idea, the switching power amp. So instead of a linear transistor, we have a switching transistor. So we have two switches. How can a switch amplify our signal? Well, those are called Class B. We have Class E and Class S. Switching power amplifier get the job done because these oscillators. Think about the switching power amplifier as a swing. So if you want when you are on swing, you only need to push your swing once. You do not need to push your swing all the time. That's like analog amplifier. You just only push it, give it a push, and give it a push and a pull. And by having those two switches, you can maintain this oscillation. Yeah, that's the key. By switch, we keep this oscillation. And because we are doing switches, there is no power loss, no energy loss. In theory, there's no energy loss. In practice, we still have 10% minimum energy loss by the switching. So that's the key component, the key reason switching power amps are much more efficient. Audio switching power amp is called the Class S. You can actually buy those. They have those in the market. They have different names, confusing names. They also call it Class S, but I sometimes saw them sell as Class D. Anyway, it doesn't matter what they called. They all operate on the same principle called the PWM. So the audio signal is amplified with PWM. So your speaker, the signal came from this power amplifier is a PWM signal. The PWM signal will be averaged by your speaker. That became analog signal. So the output of this amplifier is actually binary. So the output of it, that's why the efficiency, that's how the efficiency came from. The efficiency came from the amplifier is a binary amplifier. It's switching. This binary is a PWM binary. It's not just ordinary binary. It's a PWM binary. We know PWM represent analog signals once it's averaged. So that's a basic concept of a switching power amp. This technology is relatively new, and it's still many developments. I have another textbook, excellent textbook I really enjoyed. It's called Power Electronics. This book really have a very detailed, have a very thorough coverage of all the switching power technologies. Because we are switching, and the switching is on inductors and capacitors. So once we have a switch acted on the inductors and the capacitors, we can create a completely brand new type of applications. The modern, for example, electric cars is based on this switching technology. The inverters, the DC-DC converters, is all switching technology. So, Tim, you were looking at Amazon, you'll find that $17 power supply, right?
Yeah.
Yeah. The voltage can be changed. There's a dial, change voltage. Inside is a switching DC-DC converter. So the old DC-DC converter is analog, huge amount of waste. Now you have a DC-DC converter. You can convert the voltage from 24 to 0 to 24 with over 90% efficiency. So input is 24 watts, output is 1 watts, drop goes down. That's called the buck converter. 90% efficiency. It's amazing technology. The old technology, if you go from 24 to 12, you have to waste half the power because you only use 12, the other 12 will be wasted. That's the old technology. That was when I was a student, when I studied power supply, DC power supply. That's the only power supply we studied. But today, it's all about switching. Yes.
So everything back in the day wasn't.
Everything back in the day in the 80s is not switching.
Yeah, it wasn't nothing. None of that stuff was very efficient.
Yeah, it's all terrible. Yeah, it's all wasting huge amount of power. Today, everything is switching. So once we do switching, generally we can get 90% efficiency. So that laptop charger put out 60 watts. If we use old technology, the power supply itself will need 60 watts. That will be very hot. You need a huge heat sink to dissipate the 60 watts. But today, you say you have a sealed plastic pack, lukewarm, because to put out 60 watts, only about 60 watts is wasted on the power source converter. 60 watts. 60 watts is okay. We can pump 60 watts to the laptop where it's needed. Only 6 watts is lost in the process. The old technology, 60 watts to the laptop, you need another 60 watts. Yeah. At least.
At least, yeah.
So switching technology is wonderful. I would think this will be a very important class. We should offer this. This is more important than amplifiers. For example, we've been teaching amplifier. There's no particular progress for the amplifier for past 50 years or 30 years. Nothing. But this changes significant change past 30 years, past 20 years.
Well, I hate to do this to you, but I have to go. I have to go to work.
You are my only student. You can go. I will keep recording that. Finish the recording, and yeah, Tim, you can look at the video.
Okay.
No problem. Yeah.
All right. We'll see you tomorrow.
All right. Let me keep recording, and yeah, I'll see you tomorrow.
Okay. Bye.
Mm-hmm. All right. The next topic we're going to talk about will be impedance matching. Impedance matching is another concept. That means that's typically your antenna. For transmitter, that will be a transmitter. So the idea is have maximum power to the radio. So have a maximum radio power. How can we have maximum radio power? That's a completely theoretical problem. If those two impedance match each other, then we have maximum power to the radio or to the antenna. So if your antenna want to broadcast 100 watts, and you can only get the 100 watts. So if your transmitter output 100 watts, you can only get 100 watts if the impedance is matched. If the impedance is not matched, that means you will not get this 100 watts. So if impedance doesn't match, we can add a matching network. So the concept is put something in the middle. So your antenna, your transmitter, and you have a impedance matching network. So the end idea is have maximum power to the antenna. So not wasting power here or wasting power here. Instead, put the maximum amount of power out to the radio. So the radio will have the maximum amount of range, coverage. This concept is studied very thoroughly. There is a relatively older type of matching networks. That's called L network. That's your antenna. That's your transmitter. You have a L network in between to match the impedance, and there are equations to find the inductance and capacitance in both cases. So that's one. We also have a pi network. That's a pi or T network to do the impedance matching. In this T, we have two inductors and capacitors. So we have your radio transmitter. That's your antenna. So we will not go into the details. There's another one called balance. This is a balance. The balance is a transformer. Transformer is an excellent way of matching the impedances by varying the turns ratio. So you have a primary, you have a secondary. By alter the primary, secondary turns ratio, you can match the impedance of the antenna to the impedance of your amplifier. So they also provide a couple of examples of how do we use the balance. So this is scenario number 1, use balance. The turns ratio is 1 to 1. Why we want to turns ratio 1 to 1? Because if turns ratio is 1 to 1, the impedance never changed. Impedance ZL is also ZL on the primary side. In this case, we are not doing the impedance change. We are doing the balance load. So look at this transmitter. The amplifier is balanced to unbalanced. So that's what the balance means. Balance gets named because it's balanced to unbalanced. The first 3 letters is balanced. The next 2 letters is unbalanced. So this is the primary function or the initial function of a balance. Balanced to unbalanced. Unbalanced antenna. The unbalanced antenna will be a vertical antenna. You will see quite often. So that's an unbalanced antenna. All are unbalanced to balanced. This is put it alternatively, you can do an unbalanced to balanced. The turns ratio is 1 to 1. So turns ratio 1. You can also do turns ratio, for example, 1 to 4 turns ratio, 1 to 2 turns ratio. And to do a 1 to 2 turns ratio, you will multiply the impedance by 4. So you will change the impedance to match. Not only you do the balance, you also multiply the impedance. So the impedance of the antenna will be varied to match the impedance of your amplifier. So that's a balance. For matching impedance, there are many different ways. Balance is one way to do it. Balance. Or we can use a pi. You can use a t. You can use a l. Pi, t, or l. Each have a lot of details to do the matching. That's a lot of detail, but we will just skip the detail. Get the concept. The concept is make the impedance match. Make the power, maximum power to the antenna, and get the maximum coverage. All right, now move to the last topic. Last topic will be 2 examples of a transformer transmitter. The author provide 2 transformer, 2 transmitter. There's glares on my camera. So put the book here. Cover the glare. Okay, the last topic will 2 examples. The first example is a short-range wireless transformer transmitter. The second is a modern transmitter. So a classic and a modern. Both are digital, by the way. Both are sending out digital signal. So let's first look at a classic one, then look at a modern one. So this is a classic digital radio. So we are sending out digital. The digital data came from here, from a computer. So the binary data enters here, and this radio will do a FSK. FSK means freeze FSK. So this is a FSK radio. It will frequency modulate the carrier. So the carrier will be frequency modulated by zeros and ones. So if you have a 0, the carrier frequency will increase. For example, 10 kilohertz. If it's 0, the carrier frequency will decrease 10 kilohertz. So it will flip-flopping between above 10 kilohertz above and 10 kilohertz below the carrier frequency. This is done by this FSK data. FSK modulate the oscillator. So the oscillator frequency will go up and down depend on the zeros and ones. So we have 0, output frequency will be up. We have 1, the oscillator frequency will be down. And then we go to a synthesizer. Why go into synthesizer? To generate the carrier frequency we really wanted. So this oscillator is not oscillating at the carrier frequency. It's oscillating at a different frequency, a much lower frequency. Once we modulate our carrier, and then we use this synthesizer to make the frequency shift to the exact carrier frequency we wanted. So this is a PLL device. This PLL device will shift our frequency to the exact frequency we want it to be by a division and by two multiplications. So this will be multiplied 64 times the frequency. 64 times. So if a carrier frequency here, whatever, it will multiply 60 times the frequency. It will division here means multiplication forward. So after the multiplication, we get our carrier frequency, then we do a power amp. After power amp, we do a impedance matching. This is a L, look like a L type matching, L network. After the L network matching goes to a 5 ohm antenna load. So the maximum power will be delivered to the antenna. So this is the first example. It's a free-scale MS. This is the UHF transmitter. The second video is a QAM video. It's a mod. QAM is like we said, the most common modulating method used for data communication, including 4G, 5G, cell phone, the latest 5G, still use QAM. So this is how QAM do the work. First, if we have two modulators, the two modulator is AM modulator number 1, AM modulator number 2. So we have two AM modulator. The output of this is cosine, the output of this is sine. And then they are add together. So this is the addition. After they add together, go to the power end. After the power end, it goes to the antenna. So the antenna is broadcasting a cosine plus sine. So that's where the QAM is. So the output is a QAM because they are cosine plus sine. The modulating signal for the cosine and the modulating signal for the sine are called Q's and I's. So we have I at the top, we have Q at the bottom half. So I signal and the Q signal. How did we get I signal and the Q signal? The I signal came from digital to analog converter. So does Q signal. So if this digital to analog converter is a 5-bit, the second one is also 5-bit. So 5-bit, 5, not 5-bit, 9-bit, for example. I choose 9-bit as example. If we have a 9-bit analog, digital to analog converter, so 9-bit and another 9-bit, so what will be the I signal? The I signal will have 512 levels. So does the Q signal, 512 levels. 5-bit. I change it to 5-bit again. So not 9-bit. So 5-bit, we will have how much? 32, right? 32 levels. So we will have 32 levels, 32 levels. So 32 levels will be the I signal will AM modulate. So what is the levels for this AM modulation? Again, 32 levels. So this AM signal cosine will have 32 levels. How about the Q? Q came from this digital analog converter, 32 levels here. So after the modulation, the sine will have 32 levels. So here my final question. 32 levels of cosine plus 32 levels of sine. What is the result? 32 levels of cosine mathematically add is equals to 1024 QAM. So that's how we generate 1024 QAM is by add 32 levels of cosine with 32 levels of sine. So think about it. This will be the cosine. This will be the sine. The cosine will have 32 levels. Sine will also have 32 levels. And you put it together, you will have 32 by 32 matrix. 32. So what is 32 by 32 matrix? Equal to 1024 QAM. So that's how the 1024 QAM gets its name. The 1024 QAM gets name because in this pattern, two-dimensional pattern, if we use cosine as horizontal, sine as vertical, you have 32 levels of horizontal, you have 32 levels of sine, and combined together, you will have a two-dimensional pattern with 1,000 results, 1,000 potential results. So that is 1024 QAM. That's how it got the name. So you have a 5-bit. By having a 5-bit analog digital analog converter, another 5-bit digital analog converter, we get 32 levels of cosine AM. We have 32 levels of sine AM, and then we add them together. Magic happens. We got 1024 QAM when we add them together. So that will be the computer. This part is a interface with computer. So the radio will interface with the computer through a standard interface. In this case, is a 4-wire. If you took my other class, you may familiar with a 4-wire. It's called SPI interface. So this SPI interface is standard interface. So the radio will have SPI interface with your computer. So the data will come from here. Data will be pumped out two directions. And then the data will go through this demultiplexer. So if the original data is 10 bits, 10,000 BPS, and then divided by 5K BP. on the I's and the Q's, I's and Q's. And then this 5K BPS will combine together as QAM. So the radio will send out combined is still 10K BPS. So whatever data you send it out, the computer send it out over here, will be divided half and half, and then add together as QAM. So the receiver will pick up the QAM, will demodulate, get 5Ki BPS, and get 5K BPS Q, and combine them together again to get original 10K BPS signal. That's a QAM technology. I mentioned this technology is used on everywhere. For example, 4G cell phone signal, or cable modem, DSL cable, or Wi-Fi. They all use QAM. This latest 5G cell phone, they all use QAM with a little variation. So, for example, they have 64 QAM. By 64, it means 8 by 8 pattern. 8 by 8. So 8 by 8 means 8864 QAM. But instead of having a single QAM channel, they have multiple QAM channels. 64 QAM, 64 QAM, and 64 QAM. Not necessarily 64. We might have 1024 QAM. That will be 32 by 32 if there's a 1000. But anyway, the QAM can be different. The newer technologies, 5G for example, each QAM channel has more patterns. In this case, 4G for example, each QAM only has 64 patterns. But by having, for example, 64 channels, by having 64 QAM channels, we can significantly increase the speed, how fast they can pump in data, because each channel can pump certain amount of data at a certain speed. If you have 64 channels, you multiply that data rate by 64 times. That's how the modern 4G cell phone, the DSL modem, the cable modem, the Wi-Fi, the newer Wi-Fi type N, type B, type the new Wi-Fi, and also 5G. They all have more and more QAM channels. For example, 1024 channels. So what happens if you have 1024 channels? You will multiply the data rate 1024 times, because every channel is like a single lane highway. So if you have a double 2-lane highway, you double the traffic. If you have a 4-lane highway, you quadruple the traffic. If you have 1000 lane highway, your traffic can be 1000 times. And then this pattern gets higher and higher. Not only the channel get higher and higher, the QAM pattern get higher and higher. Originally it started at 4 patterns, or 8 patterns, or 16 patterns, or 64 patterns. Now we go to 1024. So by have more patterns, each channel can pump more data. So every channel, by having more QAM patterns, you can pump more data. So previously, for example, 10K BPS for 64 patterns. But if we go to 1024 pattern, how many more data can you carry? Everything else is the same, just by having more QAM patterns. This is 2 to the power of 6, right? This is 2 to the power. Let's use the 248. If we change 248, it's a 12 bluntly. So 12. So you will double, right? You will double the amount of, yeah, you will double. So you have 20K BPS. Yeah, just simply by having patterns goes from 64 patterns to 2048 patterns, you will double the bandwidth of each channel, QAM channel. So if you double the bandwidth, so more patterns obviously better. This represents 12 bits of data. This represents 6 bits of data. So this represents 12 bits of data. So yeah, by going from 64 pattern to 2048 patterns, you double the data rate. Originally it's 10K BPS, now we have 20K BPS. So this is one way to have more data. Of course, if you have more channels, if you double the channel, you will double the data rate. So that's another way to do. So this is all the modern digital radio use right now. They all use this technology. This technology is called OFDM. So the technology has a name called orthogonal frequency division multiplex. It's called frequency division multiplex is because each channel is separated by frequencies. So that's what this name gets to. Every channel has different frequency. Every channel has different frequency. So frequency division multiplex. Inside the channel is a QAM. So each channel is a QAM. So QAM. Hello? So the technology is called OFDM. What is the last letter? FDM means all the QAM channels is separated in frequency domain. Frequency domain separation. Multiplexing means separation. Frequency domain separation. So in frequency domain, QAMs are separated, every channel. What is the last letter O? Last letter O means orthogonal. Orthogonal means how to make those adjacent channels have a minimum interface. Because those frequency division multiplex, every channel are so close to each other. Every channel is very close to each other. And how do we minimize the interference between the adjacent channel? That is the last letter. By having all the QAMs orthogonal, we minimize the interference. That's the last word, orthogonal. The orthogonal came from the length of each QAM pattern. So previously we say we will have 1024 QAM patterns. Orthogonal, the last letter O means how long each QAM pattern will last. So by control how long of all these 1000 of patterns, we have 1000 QAM patterns, but we still have to decide how long each pattern lasts. If it lasts too long, we are wasting our bandwidth. If it lasts in too short, it's hard to demodulate. It turns out there is a perfect time that perfect time will call in the adjacent QM channels to have minimum interference. So you want adjacent channels right here, right here, right here, right here. So that's your channel, that's another channel, another channel. So by control how long each QM pattern lasts, we can make adjacent QM channel orthogonal. That's all I have for today, and hopefully everybody watch my video and have questions. Let's talk about it next week.